SwayamPrabha. Digital India. Educated India.
Hello. In today's lecture, we will deal with differential equation or a function type constraints, because in the last class we dealt with constraints that are of functional type, which we called also global constraints. Now we deal with local constraints, which are function type constraints. Let us start with the problem that motivated us to consider the constraints. That was the stiffest bar problem that you see here. We need to find the area of cross section, that is a of x as a function, that is our design variable here or optimization variable. We need to determine the cross section, that is cross section at any particular point x, where we wanted to minimize the strain energy, which we have written in terms of a of x and u of x and its derivative. In this case it is the first derivative, and where E is the Young's modulus. And again let us remind ourselves what is data here, what is given and what we need to find. What is given: Young's modulus of the material, length of the bar, and the loading P of x, which can be any function that varies with x, and also V star, the amount of material. So, we are trying to design a stiffest bar, the stiffest bar for given volume of material. So, V star is given to us and we are trying to find A of x. In between we have U of x, which is the state variable, and that is governed by this equation, right. In the last lecture we talked about how to deal with this type of constraints, that is this type of constraints, which are functional type constraints or global constraints, because they pertain to the entire structure. Volume, you talk about volume of the entire bar, not a little place, a small place in the bar. So, this is a global constraint or functional type of constraints, where we also introduce the corresponding Lagrange multiplier, so that we could write the Lagrangian for this problem, where the Lagrangian is, you write the objective function, which is 0 to L half. In fact, objective function is strain energy. So, actually this should not be there. Okay, let me erase that. So, objective function is the strain energy, okay, that is strain energy. So, we write that half E A u prime square dx, and whenever you have a constraint which is a functional type of constraint, there is a corresponding multiplier, which is this lambda. So, we say lambda times the constraints, which is a dx minus V star, and then we could just take the Lagrangian and it becomes like unconstrained minimization, not only with respect to A, but also with respect to U, the state variable. So, here we took the variation of Lagrangian with respect to A, that is one equation, and then variation of Lagrangian with respect to U, that is another equation, right. That is what we had discussed earlier, where the integrand, in this case if I were to write this as an integrand, we have 0 to L E A u prime square, half of it, plus lambda A, okay, all of this is integrand, and then I have minus lambda and V star with just a constant. V star is given, lambda is an unknown constant, V star is a known constant, it is a constant, and this is our integrand normal f. If I have that, then using this f, that is Lagrangian, when I say variation equal to 0, that leads us to the Euler-Lagrange equations, which we say dou f by dou a minus dou f by dou a prime, because actually a prime is not here, but I am just writing equal to 0, right. So far it is not there, because Lagrange included only the global constraint, but that is not complete. Our Lagrangian is not complete because this does not take into account our governing equation, which is a function type constraint, which is what we will discuss. That also gets added to our Lagrangian with a similar setup, where this is a constraint, this is the corresponding multiplier, we multiply them together, add it to the Lagrangian. We want to show that when you have function type constraints or local type constraints, it also leads to the concept of Lagrangian. Once you have Lagrangian, then we can do this. This gives us one equation, and similarly if I take with respect to u and dou f by dou u prime, if there were to be u double prime, you will also add that and equal to 0, you get differential equations. One equation to solve for a, other equation to solve for the adjoint variable that we would introduce, and we will find out what that is, right. So, our task today is to understand the role of the function type constraint that we have. Okay. These are the ones that we need to take. So, let us start writing a general problem of minimizing j, a functional, from x1 to x2, where f we have as a function of, let us say, y and y prime dx, where y of x is our unknown. If I now write a constraint which is function type or differential equation type of constraint, which let us call it is g as a function of g and gy prime equal to 0. If you look at this problem and ask, is it a properly posed problem, the answer would be no, because a constraint, an equality constraint, which is a differential equation. This is a differential equation. When there is a differential equation, the solution of this, if I solve, solution of this will give us y of x already, right. So, constraint itself is giving us the solution, because y of x is our unknown, we already got the solution for y of x, right. Then what are we minimizing? We want to minimize another functional j with an integrand f that depends on y and y prime. So, this is not a properly posed problem, because we do not have enough search space to search and find the minimum of our objective function, which is j. What do we do in that case? We need to introduce into the functional, okay, our j, an integrand which depends on two functions. Let us say there is a y and there is a z, and then there could be y prime, there could be z prime, and then dx. Then the unknown functions will be y of x and z of x. Much like in our bar optimization problem, we have a of x and also u of x. There should be two functions, then only we can impose a differential equation type constraint. So, now I have to say subject to a differential equation type constraint which depends on y and y prime and z and z prime equal to 0. Now, this is a properly posed problem. So, the problem that we have here is proper because we have an integrand in the functional, objective functional, which depends on two functions y and z and their derivatives. There can be any number, that generalization we have already discussed. Likewise, we got one function type constraint. This is function type constraint, or we can also call it local constraint. There are different names to it. Sometimes people call it finite subsidiary constraint, but let us understand that this constraint has to be valid over the entire domain. So, this constraint is valid over the entire domain. So, this constraint is valid over the entire domain. So, here g, which is a function of y, y prime, z, z prime, is a differential equation, but involves two functions, that is y of x as well as z of x. When you have two functions with one differential equation, we cannot determine both of them. So, then there is a space in which we can search to minimize our j. So, this is a properly posed problem, whereas this one is not. This one is not a properly posed problem, whereas this one is. So, we need to have two functions when you have a function type constraints. So, let us try to think about this problem. Now, we have a function type thing which is y. Again, whenever we want to establish necessary conditions, we need to perturb the functions. So, we will be perturbing y, let me call that hy, and then z, let me call that hz. So, this h that we have is a variation or a perturbation. Now, since we have two functions, I am using subscript y and z to differentiate the perturbation for y, perturbation for z. If we have this, how do we write this to first order? So, this will be equal to whatever it is at y and z, whatever differential equation or an algebraic equation that may be there. Okay, it is a function type constraint, plus we want to write the first order term. For the first order term, we can take the variational derivative, something we had discussed, that is, if we have an expression, a differential equation or a functional, what happens to the value of that function or functional when there is a perturbation in the function. Here we have two functions y and z. So, if I perturb, so I will have the variational derivative of g with respect to y, okay, and then there will be some error related to the perturbation in y, okay, times delta sigma y, that will be one term using the variation derivative which we had used when we dealt with the global constraints, another name for it functional type constraint. Likewise, we would have here variational derivative of this with respect to z, our second function, and some error times delta sigma z. Okay. Again, to recall what we mean by this delta sigma y, delta sigma z, what we mention is that if this is x and if I say this is from x1 to x2, let us say that I have a function, let us say this is our y of x, okay. Then there will be a perturbation around it, right, at some point. Let us say I choose an arbitrary point, here I give some perturbation. So, I will have a little blip like that, and area of that is that one we said is delta sigma y. Okay. Similarly, I can have a perturbation for z also. Let me draw for the same domain a z. Let us say this is our z of x. At this point, if there is a perturbation, then there also I will have a little blip, area of that, right, is delta sigma z. Okay. What we say is that this new function value with the changes of little thing at for y and little thing for z, when we do that, this function value should remain equal to 0. The constraint was there, right, g equal to 0 even after perturbation. So, we have the first order perturbation due to variations in y and z. At some points we are just only at one point we are perturbing, they can be different points, then we have this, right. When you have such a thing and it is equal to 0, we can express one perturbation in terms of the other. So, what we say here is this anyway is equal to 0, because if y and z are minimizers, they must satisfy the constraint. Constraint is g equal to 0, that will be satisfied. Okay. And that leaves us that we can express delta sigma z in terms of delta sigma y. So, that will give us minus del g del y, that is a variational derivative. For now we can write, later they say errors go to 0 into delta sigma y and then divided by variational derivative, this is not y, this is del g del z plus epsilon z, right. This is what we get here, because of the fact that after perturbations the constraint must be satisfied, that is why we got. Okay. Now, we use this fact that we can have one perturbation freely, okay, that is this one we can have whatever we want, then this other one gets determined. We use this fact and look at the change, our change in the objective functional, that is our interest, right. That delta j, which again will be j with y plus h y and z plus h z minus j at y z. Okay. So, that one to first order term we would say it is the variational derivative of j with respect to y plus some error which we can call epsilon. This error will not be the same, but using the same symbol does not hurt, you understand from the context. Okay. So, this times delta sigma y plus due to change in the function z, that little blip we talked about, this is epsilon z delta sigma z, that is what we have, right. Now, what we do is into this delta z we substitute what we got from the constraint, because constraint again must be satisfied even after perturbation, and this first order change in this should be equal to 0 also, that gives us the necessary condition. So, what we will do now is substitute for delta sigma z what is over here, and everything then will be in terms of delta sigma y, because that is what is here. Then we say that is arbitrary, one perturbation arbitrary, then what multiplies will be equal to 0, and we will also not worry about these small errors that are there, because they will all go to 0 as your perturbation becomes smaller and smaller, which is what we use as a fact to establish necessary condition, right. So, now looking at this, all right. So, we are going to continue with this and say that delta j by delta y, I will not put the error. So, this error I am not going to write now, that is delta sigma y plus and then delta j delta z, again I am not going to write this error, because that goes to 0 as perturbation becomes smaller and smaller, but we will make this change delta sigma z here, we would like to substitute what we have over there, okay, which is delta g delta y with a minus sign, right. So, that we will write minus delta g delta y divided by delta g delta z. We are not writing the errors anymore, and this will be multiplied by delta sigma y also. We eliminated delta sigma z with this and make it equal to 0, because to first order objective function should also not change. And since this thing is arbitrary, we say what multiplies it is equal to 0. So, this implies delta j plus delta y. Now, we will make the trick or whatever notation that we used earlier, including the negative sign. So, this whole thing, okay, I would call it lambda of x. Earlier it was a capital lambda and we said it is a constant, unknown constant, where now we are making it an unknown function. That is because whatever we have written is valid for all points in the domain, because the point that we chose, if we go back, yeah, this point that we chose here or here, we could have chosen anywhere. So, this should be true for all points in the domain. So, this equation is valid for not just globally for the whole thing, this is the local constraints consequence, valid for all points in the domain, all points in the domain x1 to x2, in the domain x1 to x2. Okay. So, consequently this becomes a function. Okay. So, now we would write this as lambda times delta g by delta y equal, well, this times we have delta sigma y equal to 0. Since this is arbitrary, we can choose our perturbation, one perturbation any which way we want, then that makes this equal to 0. Okay. So, we get the variational derivative of the objective function plus lambda times variational derivative of the constraint equal to 0. So, that is one equation. Okay. Now, if we look at this one, which is in this orange thing here. Okay. So, what does that say? That says delta j delta z, variation of j with respect to z, okay, divided by, with the minus sign, divided by variation derivative of g with respect to z. Okay. We are calling this lambda of x, right. So, this gives us variation derivative with respect to z plus, because this minus is there and we are taking to the other side. Okay. So, that becomes lambda times delta g delta z equal to 0. Now, if you look at, if we call this equation A, we call this equation B, you see these equations A and B are identical in the sense that we have y here, whereas here we have z, otherwise their form is similar. So, when you have two functions at all points in the domain, we should have both of these true, right. That gives us the necessary condition. That also tells us that if we were to add to the Lagrangian, okay, so whatever we had from x1 to x2, I had f, right. To that f, I can now add lambda times g. If I define it like this, okay. Now, if I write the variational derivative of this with respect to y, I get one equation, because now we have extremization of the Lagrangian, we get that equation, and then I get variational derivative of that with respect to z equal to 0, or all Lagrange equations or variation. If you do that, this gives us that equation, okay, and this gives us this equation. Okay. So, we have both of these equations coming if we write this Lagrangian. Okay. So, this way we can deal with local or function type constraint. This local function g can be just an algebraic function, it can be a differential equation, it can be an integral equation, as long as it is local. When it is integral equation, I do not mean a functional, but there could be integrals in it, but it is valid at points where integral algebraic equation. So, something an equation that is valid for every point in the domain. Okay. So, with this let us recapitulate what we have discussed so far for constraints. So, if I have a general problem, minimize y of x, z of x, two functions, and a functional j which is f, it depends on y, z, y prime, z prime, y double prime, z double prime, and so on, any number of derivatives does not matter, okay, subject to constraints. Let us say if I have a functional type constraints which we have called k with integrand j that depends on y, z, y prime, z prime, and so forth, any number of derivatives equal to 0. And now we have also discussed a case where we have algebraic or differential equation type of constraints, again any number of derivatives. What we need to do is first denote with an uppercase Greek letter like lambda for global constraint, that is an unknown constant, whereas unknown function for a local constraint. Once again, this is a global constraint, this is a local constraint, okay, global or functional type, okay, functional type, and this is a function type constraint, right. So, how do we deal with this? It is very easy, all we have to do is write the Lagrangian, so that we have j plus lambda times k plus, I should not say lambda times g, if I write lambda times g, it will be for particular value of x, I have to integrate it, actually it will be from x1 to x2 lambda times g times dx, okay. That is something we should note, the difference between our global constraints and local. Local constraints have to be integrated because they are point wise constraints, they are local, they are at different points. So, we need to integrate it, okay. Once we have this Lagrangian, we can directly write Lagrange equations for the Lagrangian, and we can write boundary conditions, and that will take over. So, any number of derivatives are fine, any number of functions is fine, and any number of global constraints are fine, and some number of local constraints should be, number of local constraints should be 1 less than the number of functions that we have, otherwise we cannot solve, okay. We will pause here and come back and solve a problem.